we're going to keep going through the LIGO and get into how we can overcome sort of these standard quantum limited noise issues using, I believe, squeeze states and squeeze light. So thank you very much. Take it away, Vicky.
All right. Thanks. And again, so we'll just keep going through this. And then if we end early, we'll do a tiny bit into quantum sensing with atoms. But let's go for, like Justin said, how we can use squeeze light to overcome the standard quantum limit. And like specifically, we are an observatory, so we're always only thinking about stuff in relation to, detecting astrophysical compact objects, right? So our ultimate goal is always detecting new physics, searching for new stuff, observing. And I think that's a just useful thing to keep in mind, because I think in the broader sense of quantum sensing, there are a lot of experiments, and there's kind of this whole subfield of quantum sensing that is quantum optomechanics. Quantum optomechanics is essentially the problem that we just laid it out for LIGO, which is a photon hits a floppy object, the object recoils. Can you ever sense the position of this object better than that recoil limit? That's like one of the cruxes of the problem in terms of quantum optomechanics as a subfield. A very typical way that people approach that problem is they say, let's put our experiment into a regime where we really magnify the quantum effects, right? How do you do this? You have like a micro cantilever with a little bit of power on it, right? The cantilever has a very, very high resonance frequency, and you can ring it up, and then you can see the mechanical resonance of like this floppy cavity mirror like this. That's a pretty typical setup for quantum optomechanics. Maybe in a circuit setup, what you'd have is like a mechanical membrane driven at some RF frequency. That's also a typical setup. The main point being that those typical experiments in quantum optomechanics, they use very, very light and small objects, like maybe nanogram style or microgram style objects, in order to observe optomechanical effects that are related to a single photon, imparting a single photon of recoil and measuring the displacement. But like, again, because this is LIGO, we're kind of in some sense not interested in how a photon interacts with the thing and how the thing moves. We see that as kind of like a problem, right? So that's a lot of the context for this. It's because it's a problem that we must overcome to sense things better. And we are not inherently trying to study that interaction per se, but just in general, in the context of quantum sensing and optomechanics, a big goal of optomechanics is to observe the SQL at room temperature. Just simply observing this limit is a big deal for a tabletop optomechanics experiment. A lot of optomechanics experiments want to overcome this to demonstrate sub-SQL, that sensitivity better than the SQL. That's a major goal in quantum optomechanics, and usually they use very small objects to exaggerate the SQL, and then they play with it in that regime on a tabletop, right? So what we're doing now in LIGO today is that we've already overcome this and installed it into our observatories for astrophysical observing during a live observing run. So this is like a typical thing that people do on a tabletop that we are basically forced to do at scale now for observing. That's a little bit of the context, but just to acknowledge there's a whole field in quantum sensing that's just studying how this works, trying to observe it, and trying to overcome it in certain regimes. Okay, and again, the two kind of parts of the field that we're talking about are shot noise and precision noise. It's timing fluctuations, the photon and the photodetector. That, because power is photons per second, random timing fluctuations lead to random power measurements per second, so that's shot noise and precision noise. Back action noise of using photons to probe a thing. Again, you hit a floppy object, it moves. That's noise. So for LIGO, we have very heavy mirrors as the kind of 0th order classical solution to this SQL problem. Okay, so it was pointed out a long time ago that we're talking about these vacuum fluctuations. Where in the interferometer does it matter, right? There's vacuum fluctuations going on everywhere all the time, right? But the real ones that matter are the ones, because we have the photodetector at the output port of the interferometer, The vacuum fluctuations that matter are the vacuum fluctuations that beat with the light that we're measuring on our photodetectors. That's to say the vacuum fluctuations at the photodetector matter, so the vacuum fluctuations at the output port of the interferometer matter. That's why we send in squeeze vacuum at the output port so that we can detect squeeze vacuum along with the signal that leaks out of the interferometer. And just to highlight again, what is the general point of what we're trying to do? First, we start with a signal like this, right? There's a sine wave, but then there's a ton of noise. Your SNR in this first example is very bad, right? We want to reduce the quantum noise. If we reduce the quantum noise and the quantum noise is the main limiting noise source, then we'll be able to, have the signal size obviously never changes, right? All that we can change is the noise. So for the same signal, we reduce the noise, and then what you can see is we start to recover signal-to-noise ratio. That is, we start to actually resolve the signal. So that's kind of maybe just some general, that's what we're going for. And when we talk about quantum noise, typical vacuum fluctuations are just sort of evenly distributed in amplitude and phase. There's the Heisenberg uncertainty. If you were to talk about the noise of amplitude and phase noise, there's just kind of equal parts amplitude noise and equal parts phase noise, right? So if what we're trying to measure here is this coherent field, the coherent laser beam that leaks out of the interferometer, the way vacuum noise looks in that context is it's like this uniformly distributed fuzz around the sine wave. That's typical vacuum quantum noise on top of a sine wave that we're trying to measure as our amplitude signal. That's the power on the photodetector. And so this was all pointed out a very long time ago in the 80s by Carlton Caves. Sort of a famous paper, just quantum noise in an interferometer. And this is essentially still the game that we're playing today, 40 years later, is quantum noise in an interferometer and how to reduce it. I won't talk too much about the math, but just to kind of lay it out for you, you have the electromagnetic field. We talked about using field quadratures or power. You can use any things you want, but I think for this case, we're going to talk in terms of the field operators because we want to, again, talk about how we manipulate different the noise in different parts of the electromagnetic field. So we'll talk about that. Essentially, what you do is you say the electromagnetic field has two orthogonal components, right, two different operators. For electrical engineers, I don't know if people think about IQ demodulation, you demodulate with respect to the cosine and the sine part of the field. That is textbook quadrature squeezing. It's just IQ demodulation of an electromagnetic field. And when you parametrically plot the demodulated I and Q, what you'll see is an ellipse. That's squeezing compared to a circle, which is unsqueezed. Uncorrelated noise versus correlated noise. So once you quantize the electromagnetic field, you can talk about it as cosine and sine, x and p, creation and annihilation operators. However you want to lay out your basis is totally valid. That's to say whether you want to talk about it in the wave picture or the particle picture of photons, all totally fine. The main thing to note is that cosine and sine have a phase relation. Position and momentum have a phase relation, right? They're like the derivative of one another. That means that because these two variables are correlated, it imposes an uncertainty principle in terms of the noise of both things. You cannot perfectly define one or another because a measurement of one affects the measurement of the other. Again, just relaying out the quantum measurement problem in this context. So when you write the electromagnetic field, the field quadratures become field operators. You can quantize that. There's the uncertainty relation, and maybe this is something I stole from my grad student's thesis. Maybe electrical engineers are familiar with phasor diagrams of how you represent a field. So if I have a coherent state, that's for example the state that comes out of a laser, it's a sine wave with some amplitude. What that means is that there's a line, there's a stick. The fuzz, that uniformly distributed fuzz on top of a sine wave, that's the circle representing equal amounts of noise in both of the quadratures, right? Coherent vacuum, it's the same thing. There's just no average displacement of the field. There's no average field value in other than half h bar omega, obviously, because the line has finite thickness for the vacuum state, right? Half h bar omega. So what you can then do is talk about phase squeezing, for example. Phase squeezing, first let's just talk about generally squeezed vacuum, right? Squeezed vacuum by itself is these two things here. I'm sorry that it's kind of washed out. Inherently, you can see that phase and amplitude squeezed vacuum are essentially the same, right? It's one line, and then you have periodic bursts of noise. The way we actually achieve that is you parametrically amplify the field. We'll talk about this in a second, exactly as the quantum optics experiment there. You pump a thing, you do parametric amplification based on a pump thing. What it amounts to is you're amplifying the field twice a cycle. That has a huge amount of noise when you do amplify it, but that implies if you have perfect quantum limited amplification, amplifying the field at one time implies a de-amplification of the field at other times. And that result is squeezed light. And that's what you see here, right? So for squeezed vacuum, what you see is these periodic times when noise is high. That's when the pump aligns with the incoming electric field. And then you, of course, see when it destructively interferes and the noise is low. What then determines which quadrature of the coherent state we're squeezing? It's how you sync it up. Is effectively all it amounts to. In terms of IQ demodulation, it just comes down to one demodulation phase on a phase shifter on a local oscillator. So if you line up the phase squeezing, you can line this up to interfere away quantum noise, kind of mid-fringe right here where you're phase sensitive. You can also line up squeezed vacuum to interfere away amplitude noise. So reduce the noise at the top of the fringe, reduce amplitude noise, or reduce noise mid-fringe, reduce phase noise. And again, that's just a matter of how you sync up these two different lasers, how you sync up the laser that drives the squeeze light, and how you sync up that relative to the phase of the local oscillator. That is your displacement measurement. That's the power out of the interferometer. Okay, so once you do squeeze vacuum, don't need to read too much into this. Maybe the main component I want to point out here is that typically we talk about squeezing in terms of a squeeze factor. And what that means is that for the cosine and the sine components of the field here, we de-amplify one component of the field by e to the minus r. And this convention is terrible because half the people call it r, half the people call it 2r. It doesn't really matter how you do this. So you de-amplify one component of the field, for example, de-amplify the cosine by e to the minus r. That implies an amplification of the conjugate quadrature, the 90-degree shifted. So if you're cosine and sine, you will amplify this noise in the orthogonal quadrature by e to the plus r. And what you see here in terms of the noise ellipse is, again, this de-amplification by e to the minus r, along with this amplification here of e to the plus r. When the pump syncs up to amplify noise, and one quadrature, it shrinks the ellipse because you're amplifying this one, which shrinks the ellipse into the circle into an ellipse. And then what you do is you then put this through a beam splitter to combine it with your coherent tone. That's how you get what we call a bright squeeze state. That's how you get the sine wave. You have a beam splitter, squeeze light comes in, and then so does the coherent tone. It also comes in. Then what you detect on a photodetector is a bright field plus a squeezed vacuum field. That's how we inject squeezing. And something I want to point out is that I'm calling this squeezed vacuum, but squeezed vacuum is not a zero photon state, right? You're putting energy into a pump, and you're creating a laser beam with correlated photon pairs. We'll talk about that in a second. But for example, if you generate about 20 dB of squeezed light, what you're talking about is the ellipticity of the error ellipse. That's what 20 dB of squeezed light means. It's a statement about this major versus minor axis of this noise ellipse. And depending on how much squeezing you're generating, the average photon number in the squeezed field is not zero, right? It takes photons to squeeze the vacuum. One way people say this is it's kind of a complex vacuum state. We'll talk more about this in a second, but I just want to make this point that this is really engineering the dark field, right? This is engineering the dark port at the output of the interferometer. When we combine this field, this dark field, the squeezed dark field, with the coherent tone we're trying to measure here, that's the stick. You have the typical photon number for a coherent state, alpha, plus the number of photons in the dark field, sinh squared of the squeeze factor. And for about 40 milliwatts of laser power, which is what we detect right now, there's about 10 to the 16 photons in that field, if you just work out the math. And what we're doing is injecting an additional 10 correlated photons. That's we're ejecting about 5 photon pairs that are correlated. And that is how we are changing the noise properties of our measurement of this 40 milliwatts. Yeah.
I'm wondering if I'm understanding this, if I say this from a different perspective.
Yeah.
If you squeeze the eye field, if you squeeze the eye samples, you get a gain on the Q in the signal-to-noise ratio, and vice versa.
You amplify Q in order to de-amplify I. Exactly. In the noise. Depending on how you line it up. If you line up that to create phase squeezing, which is just a statement about you have squeezed vacuum, right? That's the ellipse. But how do you line up the ellipse with the stick, essentially? I'll have some more like photos about that. Let me just show you those photos really quick right now, actually. So if you look here, right, you can line up this to produce phase squeezing or produce amplitude squeezing, right? All the squeezed light source does is it produces squeezed vacuum, which is these little blobs, right? But you can have that destructively or constructively interfere with the coherent field however you want, right? You can have that be phase squeezing. That is to say, compared to where, like there's when you control the squeezing angle, you can set like, off just like all right, it amounts to a demodulation phase. Are you applying this to the I field of the local oscillator or the Q field of the local oscillator?
Correct.
Yeah, exactly, yeah. But inherently on its own, squeezed vacuum is just these blobs until you line it up. Yeah, that relative phasing is what determines how much noise is coming into what you're measuring. Another way to say this is like if you look at phase squeezing here, right, what we're measuring for like LIGO, for example, is the amount of power, right? So we can either put the noise ellipse such that we get a really good measurement of this angle, or such that we get a really good measurement of the length of the stick. And I don't know if the phasers are more intuitive or not, but you can line up the phase of the squeezed vacuum ellipse compared to your local oscillator tone however you want. And that determines the squeezed quadrature. Yeah. Okay, so we can go a little bit more into squeezing right now. So just in terms of the squeezed vacuum source, we use a nonlinear optical crystal, PPKTP. We put in a green pump photon. It gets spontaneously down converted into a pair of 1064 nanometer photons. That's a carrier frequency for us. That's the main LIGO laser frequency. This is like just like the experiment that we had yesterday in the quantum optics lab, except I think that was probably type 1. It's type 1, right? SPDC, spontaneous parametric down conversion. And the difference between the different types is just like, you know, you have one pump photon, a vacuum fluctuation comes by, it gets spontaneously down converted into a pair of red. And it's just like, what is the relationship of these two down converted photons? What is the relationship of the signal and idler? So in this type of SPDC, we do fully degenerate, meaning that they go in the same direction, they're the same polarization. The two signal and idler photons are like 100% degenerate. You can't tell them apart other than they're at different frequencies, right? Because in nonlinear optics, we're driving the second nonlinearity here. You know, you send an e to the I omega, the pump produces e to the minus I omega, so you get the conjugate sideband and frequency. But otherwise, the photons are like totally indistinguishable. They go the same direction, they have the same polarization. Other than frequency, there's no difference. And so you can see here, just like mapping, you know, this little box, if you took a cool photo of it, it would be this one. So here is the nonlinear crystal. It's like 1 millimeter tall, 5 millimeters height, and then the length is about 10 millimeters, so it's about centimeters. So this is a pretty small crystal. These are 1/2-inch mirrors here, just like for reference. What you see is the green pump light is pumping the crystal in this cavity. You have to do that to increase the nonlinear interaction to get enough intensity to produce high amounts of squeezed light. And so there's the pump for the parametric amplifier. It pumps this nonlinear crystal. You see that lighting up the crystal. And actually, like for a material scientist, a big problem we're working on right now is, you know, it takes pretty high laser intensities to take this nonlinear, to drive the second order nonlinearity, and that has consequences for like material damage. And so finding damage resistant or higher damage threshold optical materials that are incredibly low loss is a big challenge for LIGO. Because the more squeezing we want to operate it with, the more green power we're going to have. Green power degrades materials very fast. And that translates into like both operational issues and also just like loss, which we'll talk about. But yeah, just a cool photo. You can see why green damage is a big problem for us. Okay, the squeeze light source, we line it up. We can do phase squeezing here, or we can do amplitude squeezing where we reduce the noise at the peaks and the troughs depending on how we set that demodulation phase. More broadly, we call that the squeezing angle. And I thought maybe it could be fun to do a quick little tutorial on tabletop squeezing. So this is just to make it really, really concrete. What typically happens in a squeezer setup? You typically have a laser. You do second harmonic generation to go from 1064 to 532. You get green light. You take that green light. You use it to pump your parametric oscillator, your parametric amplifier. That generates squeezed photon pairs. You have a local oscillator from effectively the same laser that you beat it with, and you detect imbalanced homodyne detection. This is a typical squeezing setup. Typically when you do this, and you do balanced homodyne detection, what you'll see in the differential port of that is that you'll see, for example, the shot noise limit, depending on, E times the number of charge carriers, like the number of photoelectrons you have per second, effectively will define your shot noise limit, right? So you know your laser power, you know how many milliamps you're measuring your photodetectors, you know what the shot noise limited photocurrent noise is. From there, you add squeeze vacuum. You just overlap squeeze vacuum right on top of your local oscillator here. So here, the local oscillator is like the blue one. If you add squeeze vacuum, you can change that demodulation phase. Again, like if you're reading out with the error ellipse all in your measurement quadrature, or else it's orthogonal to your measurement quadrature, so there's less noise. If the noise is all in your orthogonal, or if all the noise from the squeeze light is in your measurement quadrature, that's you're doing anti-squeezing, you'll see green. So what actually happens is you have local oscillator shot noise, you add squeezing. You can turn the demodulation angle such that you see the full noise power from squeezing. You can turn it the opposite way such that you start to see noise reduction from squeezing. You can just let that demodulation angle drift around in the ball and the stick, and what you'll see is these kind of McDonald curves of going from anti-squeezing to squeezing to anti-squeezing, squeezing as you drive this error ellipse around your stick. So you can see all of that. Why is it like this? Okay, then what we would typically do is you'd measure how much nonlinear gain am I driving? Yeah.
I have a question.
Yeah.
From an experimentalist. What knob are you turning?
The relative phase of the local oscillator compared to the pump light into the parametric oscillator, parametric amplifier, which usually amounts to just like a demodulation phase on a signal generator or something like that. Yeah. Yes. Yep. So then, right, so you generally know what your pump parameter is. As you know, like you have a parametric amplifier, that will go into parametric oscillation at some point. You try to see, where am I compared to that threshold power where it oscillates. Then you calculate the noise variance. And so there's some references I'll have at the end if you're interested, but basically you just calculate the noise variance. It goes up or down depending on if you're squeezing or anti-squeezing, that is if you're green or red. And it depends on this parameter, which is effectively just, this is the loss. And there's also some mixing between, noise from the sine. The noise adding quadrature can get mixed with the noise reducing quadrature if your phase of syncing up the local oscillator and the squeezing is not perfect. That jitter noise of the ellipse will also create noise. But what you always end up with is this. You'll always see essentially more anti-squeezing than you see squeezing. And the reason for that is loss. It's very easy to see all the noise from all the photon pairs if they're kind of uncontrolled, but it's hard to maintain that when you try to bring it sub-shot noise. And so that leads to this asymmetry here between squeezing and anti-squeezing, and the difference there is loss. So here you might be generating almost 15 dB of squeeze light. That's to say your ellipticity is about 15 dB, but you'll never measure that effectively because of loss. And so a lot of the challenge in actually implementing squeezing and getting it working and getting a break even where squeezing is reducing more noise than it's adding is about controlling loss. And that's like a whole part of the game in terms of, I think, the deployment of quantum systems into real applications. Most things will end up loss limited. And this is how we kind of see that asymmetry. And we know we're generating this many squeezed pairs, but we cannot detect all those squeezed pairs symmetrically. Okay, so we'll go back to LIGO and how does this look in LIGO. So, we showed that the total detector noise is kind of shot noise at high frequencies. Out here, that's where the detector is not that resonant, not that sensitive. And so the reason shot noise is not flat is because this is a calibration of, milliamps per root hertz of shot noise into displacement noise. And that takes into account like how, what is the resonant enhancement of the displacement noise, because LIGO is a bunch of cavities. It's not sensitive to noise at the end mirrors at every frequency. It's not equally sensitive. And so we're much more sensitive to low frequency fluctuations, for example, like quantum radiation pressure is really low frequency, and that's because the arm cavities are resonant for about 40 hertz. That's the bandwidth of the arm cavities. That's why quantum radiation pressure noise, we're excessively sensitive here, because to boost our power up, we have to make the arm cavities have a lot of resonant power enhancement. And the reason it ticks up over here is because once the arm cavities are getting like a lot of power enhancement for 40 hertz, like again, we saw before, signals are at 100 hertz. So 40 hertz is like a totally inadequate sensing bandwidth for gravitational waves. So then we have to add signal recycling. That broadens us from not 40 hertz, but out to about 450 hertz. And beyond that, shot noise is this flat line because we lose displacement sensitivity for the same milliamps on the photodetector that we measure. And you'll see a lot of these tones here. This is probably a stray 60 hertz line, but a lot of these other ones are vibration modes in the strings or calibration tones. Because a big problem, this is a big problem in optomechanics generally, is like, how do you know what your displacement sensitivity is? That calibration is actually very hard to do, and we do it in real time. We have a whole calibration team that manages calibration. Like, all I know at the end of the day is I measure milliamps per frequency, right, on a photodetector. That's all experimentalists know. But how do we know what is the corresponding, picometers per root hertz of that? That's the job of calibration. So we drive the end mirrors and we look at the line heights in our displacement spectrum, and we have a NIST, we work with NIST on the calibration of that photon drive at the end mirror. So we do photon calibration of the displacement. And those are tones that are injected in real time. So we're always monitoring the line heights, and if the line heights go down, that's because somehow our detector configuration has changed and we're now less sensitive there, likely because something has misaligned because of the temperature or because of something. So real-time calibration is a challenge. Anyways, all this is to say that shot noise on a photodetector is flat, but calibrated into displacement sensitivity, it is not flat because we're not equally sensitive at all frequencies, and shot noise is flat in milliamps. Okay, let's get past this for now. So let me just show you this first. So in 2019, we did the first injection of squeezed light into LIGO interferometers, and that was just exactly what you see here. That squeezed light cavity was installed at the output port of the interferometer, and we saw basically exactly this, and we quantified this in the noise by saying, so here, we block the squeezed light beam. There's literally just a button, you press, it downs a flipper that dumps the squeezed beam. That's it. It's just a flipper mirror on a motorized flipper mirror. That's it. So if we deflect the squeezing beam away, that is, we have no squeezing, the detector noise is as it is in the black trace over here. Again, you want less noise, right? So then we add in squeezing, we open that flipper mirror, squeezing is injected into the interferometer and measured at the photodetector, and we see that this noise goes down. That's great. That's the effect we want, that you inject squeezing and you set the phase to be in a noise reducing quadrature, your noise goes down. So then we go from the black to the green curve, and this here is about 3 dB. That's about a 2-fold noise power reduction of your shot noise limited sensitivity. Sorry to say in that complicated way, but of course, whenever you add squeezing, you're adding photons, you're never reducing power, right? So you're only reducing you're only improving your sensitivity, but not your noise power in absolute terms. Okay, So here, right, you inject squeeze light, your noise power goes down, or your sensitivity increases, so your noise effectively and strain goes down. But what you see then is the conjugate side. So this was kind of the first sign that, like, yeah, we see some quantum back action happening now, right? Because we're reducing the phase noise here. We're sending in phase squeeze light that successfully reduces shot noise limits. But then, of course, like what we're sensing now is that this excess amplitude noise is creating an additional drive on our mirrors. And that is resonating in our interferometer below 40 hertz, which is why kind of over here, below 40 hertz, when we inject squeezing in green, we see excess noise compared to in black when there's no squeezing. That was the first sign of basically like, yeah, even 40 kilogram mirrors can mechanically recoil from this 10 correlated photon noise drive that goes to one arm and not the other. So then we knew, we have to do better, right? So what we really want is we still want to always be reducing shot noise at high frequencies, but what we also want to do is reduce this quantum radiation pressure noise, this amplitude noise at low frequencies. How do you reduce amplitude noise? You inject amplitude squeeze light. That is, it's lined up to be in the squeezing is lined up to be in the amplitude quadrature at low frequencies, while still being in the shot noise phase quadrature at high frequencies. And this is what we call frequency-dependent squeezing, because we want to change the squeeze quadrature as a function of frequency, because we understand that different quadratures of the field limit us at different frequencies due to how the detector operates. The way we do this is complicated. I'll say it really quick and then show some photos. But again, we have the squeeze light source that goes to the output Faraday. And to say this is something that we kind of got installed and started working in May of 2023. The initial injection of squeeze light was 2019 to 2020. We went down for a 3-year observing run to install frequency-dependent squeezing and came back online in May of 2023, and that's still the run that we're ongoing in right now. Yeah, so we actually ended up like doing some serious improvements to the squeeze light source from the 3rd observing run. And the most important thing is we added in this filter cavity. And what the filter cavity does is, normally squeezing, you would come in and all your noise sidebands are, they are what they are. The squeeze light source makes the conjugate, right? Because the nonlinear optical interaction will produce the conjugate sidebands of the noise sidebands. And you can kind of phase those compared to the local oscillator, however you like. What the filter cavity is going to do, it's going to select, we're going to park it on resonance with some sidebands, some signal sidebands, so that the signal sidebands are rotated with respect to the idler sidebands. And that will produce a frequency-dependent phase shift of the squeezing quadrature. That means at different frequencies, we'll be squeezing different parts of the field, right? So what we do is we reflect the squeeze light beam off this filter cavity. The filter cavity profile and reflection is effectively producing this. So when you're on resonance of the filter cavity, you'll see a 90-degree resonant phase shift. When you're off resonant, you'll just see a full phase shift. And so you have a 90-degree difference in the reflected phase on and off resonance from this cavity. And that actually gives us exactly what we're looking for, which is great, because this 90-degree phase shift is enough to take us from phase squeezing into amplitude squeezing by reflecting the squeeze beam off of a cavity that is only phase shifting, for example, the signal with respect to the idler photons. And so what we actually see is pretty cool. So again, the black one is the quantum noise this is the, detector noise that we measure without squeezing. If we kept doing the basic type of squeezing with no frequency-dependent engineering, we would get the green. So the quantum radiation pressure noise, remember that excess amplitude noise, that is really huge now because we've increased the amount of squeezing we can generate and we're increasing the laser power. And so these things kind of come to a crux. And so in the 4th observing run, if we don't use the filter cavity, what we'll see is the noise in green, where all of this is back action noise. Yeah. But what we can see is that if we turn on the filter cavity and park it correctly, we can rotate all this excess noise back into the noise reducing quadrature. So just to say that one more time, this is phase squeezing up here. If we only set it to phase squeezing, the interferometer's optomechanics will rotate phase squeezing into amplitude squeezing. And so what we do is we pre-rotate it so that we compensate the interferometer rotation. So that's what this does. We pre-rotate phase squeezing into amplitude squeezing. We send in this state so that it's amplitude squeeze light down here and phase squeeze light up here. And then we can reduce the dominant quadrature of quantum noise at every single frequency by matching our squeezing injection system to the interferometers. And so that's effectively what we do. And this is cool because, again, here's another way you can see this. Like, if you were just to adjust the squeezing angle and look at the noise, what you'd see is, like, at any given squeezing angle, I could, like, reach, I could lower the noise. Like, if I just change the squeezing angle, right? I could park it here to get phase squeezing, but I could really improve the quantum noise at 100 hertz where it matters by detuning it away from phase squeezing and choosing these other angles. And again, what you want is all the minimum uncertainty points all the time. And you can only achieve that by engineering the quadrature of squeeze light you're sending in. Okay, the rest will basically go into some photos here. So here's the filter cavity design. This is a tricky thing to design because, again, the frequency that we see here of quantum radiation pressure noise, this is really big, between like 30 and 100 hertz. That means we need an optical storage time equivalent to 30 to 100 hertz to phase shift like one set of sidebands from the conjugate sidebands. That's really hard. To get a lossless optical storage time equivalent to 45 hertz is about a 3 millisecond optical storage time. So you need to, this is like now this gets into a typical LIGO problem, right? Because I need to losslessly store photons for 3 milliseconds. That means it already can't be in air because it will scatter off of air particles. So now you're talking something in vacuum. How do you get a long storage time optically? Well, you could either have a really, really long beam tube or you could have many round trip passes, right? The problem with bouncing a laser beam around in an optical cavity is the more passes it has, the more that the surface defects and the surface loss will affect you. You have cavity enhanced loss at every mirror surface. So you can't have too many bounces because then you'll have too much loss. If you have your cavity impossibly long, it's very expensive, as you could imagine. So the parameters that we settled on was to do a 300-meter in-vacuum cavity with a bandwidth of about 75 hertz full width half max to achieve a 3 millisecond storage time to get the squeezing rotation in. So that's what we've ended up doing. And so I'll kind of show some more implementation photos now, but yeah, you basically take the squeezer, bounce it off the filter cavity, inject it into the interferometer. This is way more complicated in practice for some issues. This is like kind of a high-level overview, I would say. It's complicated for several reasons. One huge complication is the problem you guys were all bringing up earlier of how do we know what the phase of the squeeze light is? How do we know what's the phase of the pump field with respect to the local oscillator? We need control sidebands to constantly monitor and feed back to hold that distance stable, right? Because like what will change the phase of the squeeze light compared to local oscillator? If that path length, again, its interferometry moves by a quarter wavelength, you've also already changed the squeezing angle by about 90 degrees. So you can't have any jitter, which is why all of the squeezing vacuum optics are in vacuum and everything to reduce beam jitter, to reduce pointing noise. And also, this is another problem, right? Like this is a huge facility. So these are suspended mirrors in places that are easily a 5 to 10 minute walk across from each other. How are you perfectly aligning a dark field to a bright field when they're in different vacuum chambers in different places and things are thermalizing and everything is moving? That's a very hard problem. So we have a lot of things in here in the implementation of squeezing that are about controlling the alignment, automated controls of the alignment of the squeezed field compared to the main local oscillator field. This is something that on a tabletop, maybe you appreciate in the quantum optics lab, you have to constantly align one path of the interferometer to the other. We have automated systems that control all of that alignment on site because the alignments are always drifting in real time. So yeah, a lot of the alignment problems in the quantum optics lab are very familiar, and there's stuff that we have to automate for observations, as well as many other whatever things. So that we have in-air optical tables that produce all these like additional tones that we're using to sense and control the squeezing field. So we have about 2 tables like this to prepare the squeeze light. this is just a fun video to appreciate how complicated this is in practice. This was when we had to move the squeeze light source from one chamber into another chamber and recommission the squeeze light chamber. These are what you see them installing on this lift is an in-vacuum optical table on top of which we've already installed all the squeeze light optics. So yeah, this goes from here. You can see this is a pretty big operation. All the squeeze light, the core optics that the squeeze light touches all have to be vibration isolated. And again, this is an active in a vacuum vibration isolation table. In practice, when we're observing, if you were to take a photo, you'd see like this, right? You kind of see those infrared dots on a phone camera, and you see the green pump light for the OPO. And this is, what the chamber looks like if you open up a viewport and look while observing. You see that we're always pumping the OPO continuously, and there is some infrared light, but of course it's very dark. Again, that's part of engineering the dark port. When we inject squeezing, there's a flipper mirror in the middle of that table I just showed you that opens up a mirror. Then the squeeze beam goes through this tube, and then it goes from here into the interferometer. So that's this beam diverter is effectively opening up the beam to cross this tube that connects chambers. And then it goes into the interferometer, comes out of the interferometer, and the output photodetectors are in this chamber over here. So that's where we actually do all the detection of the light. And so I told you the filter cavity was complicated. It's a 300-meter in vacuum cavity that didn't fit into our facility, so we created new beam tubes, new beam tube enclosures at each of the observatories to handle this new vacuum chamber. So you can see here laying the concrete for the new beam tube enclosure of the filter cavities. This is Louisiana site, the Hanford site. This was like a whole project, you can tell, during the pandemic. That was very tedious. The filter cavity beam tube is much smaller than the arm cavities because we're not going the 4 kilometers, so the beam doesn't diffract as far, and it's not as high power, so we don't need to have a bigger beam for higher power handling to lower the intensity. And so you can see, there's a lot of people involved. I'll just point out TJ really quick. So TJ is an operator at LIGO Livingston. He was previously, when I was a graduate student at Berkeley, one of the undergraduate students in my class who went directly after graduating to work as an operator at a LIGO observatory. As well, like at Hanford, we have one newer operator who did a master's at CSU Fullerton and is now an operator with us at the Hanford site. So in terms of just like oddball career choices that students could make that are within physics, that are within quantum. TJ does a lot of different stuff, but amongst them was commissioning the filter cavity beam tube and the vacuum system for that. So there's a lot of variety in terms of what students could do, and there are, right now is not such a hot time for jobs in LIGO, but in general, there are generally lots of interesting positions for people at all different levels. We've had operators come in with PhDs, and we have operators with bachelor's degrees. Like one of our newest operators at Hanford was also a previous Berkeley undergraduate. So there's a lot of like interesting kind of oddball career opportunities at the kind of big science facilities I don't know if everybody is aware of in that way. But yeah, it's pretty cool. TJ does a whole bunch of stuff, which is kind of fun. So you can see kind of what it looks like. There's a lot of people. Drew was one of my students. Danielle here is a senior scientist. Naoki was a site postdoc. There's a bunch of, you see, there's just a bunch of people generally involved. So this definitely goes from the scale of like small tabletop little experiment to like, these were all of our students that we brought to the observatories. We trained them at MIT, brought them to the observatories, then did on-site commissioning, and I supervised the students doing on-site commissioning. So that's kind of like what it could look like, for example, like in terms of like a PhD in LIGO. This is something you could do. This is something at least my students did then. So that was very nice. And again, you see that, with no quantum enhancement, that is when you block the squeezer beam and dump it, you get the black curve. If we had typically done what we did without the filter cavity, then you see all the back action noise and the orthogonal quadrature. That's the amplitude noise getting mixed in. If we turn on the filter cavity, you see this amplitude noise get rotated back because now we're amplitude squeezing at low frequency. So we reduce the low frequency amplitude noise the same time that we reduce the high frequency phase noise. So this is really like something LIGO's been going towards for decades. Like we call this kind of, it's kind of a funny name, but we call this like broadband quantum noise reduction, right? Because we're reducing quantum noise at all of these astrophysical frequencies. But one thing that's weird to think about in terms of quantum noise reduction, I'll just show you we do this for both sites, is that like, we're calling it broadband quantum noise reduction, but if you look at the frequency scale here, this is quantum noise reduction of noise sidebands that are within 100 hertz of the carrier. So in some sense, it's very narrow band. But for LIGO, because this is our sensitive band, this is really what we need out of quantum noise reduction to reduce it at all frequencies, even when all the resonators come into play for LIGO. So that's a big part of the complication, is fighting the way the interferometer works. And anyways, it turns out this works really well. Like, we reduce successfully the quantum noise right in this astrophysically sensitive region around 100 hertz. And this is what we get in terms of detection rates. So 2019 to 2020, we just had basic squeezing. 2023 to 2025, now in our 4th observing run, with this improvement here, reducing this noise, like critically right there, just by like 10% or something. That's frequency dependent squeezing. We kind of really, really increase our astrophysical detection rates pretty dramatically. One way to see that is that in the first 3 observing runs, we observed for something like 2 years, right? And we got 90 events. And then basically in the last couple years, we've gotten 200 events. So our detection rate has increased significantly from the previous observing runs, just because we're able to reduce this little bit of noise right here. And that's a bit because, our sensitivity scales as the cube of the noise, right? So if we reduce our noise by 2-fold, we reduce the volume of the universe in which we're sensitive to gravitational waves by 8-fold. And so that's a huge improvement just from really 3 dB of measured squeezing. And you can get there with 50% loss in your system. So it's only because our position is kind of very extreme that quantum noise reduction has really like extreme yield, I would say, in terms of actual sensitivity increase. And that's enough to basically go from monthly to weekly detections now to almost daily, kind of every other day type of detections, which is very cool. So again, in the year of observing with just basic kind of squeezing, the initial step, this number's a little outdated, but just for fair comparison, something like 60 events. Now in like just over a year, there's something like 200. So this is like a huge dramatic improvement in detection rates, which is very cool. So now let me go back a little bit to this SQL part here. So as part of the SQL, right, you want to reduce the noise to the minimum possible of all these frequencies. And again, we talked about that can't be done just by uncorrelated photons in standard laser light. But there was this paper in 2001 that was like, look, if we put in squeeze light, and specifically if we put in squeeze light with a frequency-dependent squeezing angle, then we are probing not with uncorrelated typical laser photons, we're probing with correlated photons. And especially correlated photons right here, where you really confront the SQL, and the correlations here can really help you. And so, it's kind of cool that just as this paper lays out, if you calculate what the quantum noise should look like with frequency-dependent squeezing, where we engineer the input squeezing angle, that's basically exactly what we actually measure. So this was a paper here from 2001, and this is our measurement in, 2024, of how with frequency-dependent squeezing, we do kind of lower all of the noise, right? The purple compared to the black again, including if you plot here, where is the SQL? For the masses of our test masses, we're actually sensing sub-SQL at room temperature at 50 hertz by almost 3 dB, which is awesome because that's actually exactly where the astrophysical band is. And it looks exactly as predicted, which is also just very cool. My grad student was very happy. And in fact, we can flesh out this entire picture from 2001, right? If you don't have the filter cavity, we see these dips. These dips are from the arm cavity rotation of phase to amplitude squeezing. It's what happens when squeezing resonates in the arms. We can see those dips, and we can see the dips as we tune the squeezing angle everywhere here. So that's pretty cool. And what do we do next? Now, before this was just a paper on its own showing that macroscopic quantum correlations work. And now what we're doing is diagnostics, because what we can see is that these dips from frequency-independent squeezing without the filter cavity are better than the purple. Like here, we're doing better without the filter cavity than we are doing with the filter cavity, and why? So that's kind of our, yeah.
So if you reduce the noise 3 dB, you increase
exactly, yeah. Because the signal is fixed, and all we can do is reduce the noise, exactly, yeah. Yep, so then, yeah, you can see here, we're still missing it quite a bit, and that, for LIGO, is like a huge chunk of change to leave onto the table in terms of noise reduction. So we see that if we don't have the filter cavity, we're doing a lot better than with the filter cavity. So, right, if you bring that into the dB picture, so this is just saying, what is the purple compared to the black in units of decibels, that ratio. Where we're at today is about 6 dB of squeezing. It's improved a little bit since this plot. That's a 4-fold noise reduction today compared to 3-fold noise reduction in the previous run of 3 dB. The current run was 6 dB. And our goal for the next couple of years is 6 dB, but really into the astrophysical band as well. And that requires a lot of reducing the filter cavity losses and figuring out these final, how do you get squeezing in the final 100 hertz around the carrier? That's very hard. And where we're going for the next generation then is really 10 dB of squeezing, which is a lot of squeezing. That would be as if the purple line wasn't just, in the near term, we want the purple line to be flat and here and there all the time. In the future, we want this purple line to be down here at 10 dB, which you can see what that would do here. That would really drop your noise out to here. And once you're at 10 dB, then quantum noise is far below all your other technical noise sources. So this is sort of, 10 dB is like, can we make quantum noise not a problem anymore? Do we have the ability to control loss so that quantum noise is not a factor that you have to consider in terms of engineering this thing? Yeah, so you can see here is kind of, this is where it really matters astrophysically that we're missing it, this region. But even in general, even our best squeezing doesn't allow yet for 10 dB. And even already, you can see that this, not only are we missing it, we're not perfect here, but we're actually adding 5 dB of noise at 30 hertz right now with squeezing. And you can see here, compared to the total detector noise, that also is starting to matter at pretty critical frequencies as well. And so figuring this out is a problem that my group now works on. I'm gonna go past this slide. So, so here, out here, where it's kind of flat, this is just limited by losses in the system. Down here, like I talked about, this is a big problem that, we need to have better, basically, control of the back action and the losses in the filter cavity to be able to efficiently rotate it and not lose photons and not lose that squeezing effect. And in this really critical astrophysical section, right around 100 hertz, this is like a very involved thing that's kind of a lot to do with the thermal distortions and the high power handling of the full interferometer. Like I said, we're circulating like 400 kilowatts of laser power continuously. That has a lot of thermal lensing across the whole system. And having the squeezer beam mode match dynamically to a thermalizing system is still a very hard problem. And so what we're developing is diagnostics to help us be able to understand and eventually feedback control so we can change the radius of curvature accurately to compensate the distortions in the interferometer. So there's a lot of technologies that are still kind of missing from this to be able to really fully control back action, fully control losses, and just even figure out what we even need to be doing at the most important kind of spot there. Another thing we need to work on is stability. So working on sort of, how can we hold the alignment stable? Even how can we get materials for nonlinear optics that are more damage resistant at higher generated squeezing levels at higher laser intensities in the visible? That's also very hard. And of course, the biggest thing is really loss. Loss is always, in terms of quantum sensing, what kills most ideas of how to use quantum sensing to get beyond the classical best thing we can do. Loss is almost the #1 thing that will kill almost every single application everybody thinks of. Not to be pessimistic, but just to say that this is a global problem that in LIGO we're solving, but it's not just loss is not only a problem for LIGO, it's a problem for the break-even of most quantum sensing applications. How do you talk about loss? One way we can talk about loss is as a beam splitter. So if you have a squeeze state comes in, if I lose, let's say I have a 10% loss source, that's just gonna send 10% of my squeezing out into a port I'll never get back, and what comes into the unused beam splitter port is normal vacuum noise. So you lose the correlations, you add in regular vacuum noise, you replace it, and you're back to where you started, essentially. So once you lose a photon of the squeezed photon pair, you kind of end up back to where you started. To a smaller extent, It's phase noise. This is, again, if you can't hold, this is jitter and how you're lining up the squeeze vacuum source with the local oscillator. That's also a problem. And so what we do a lot in LIGO is loss hunting in the squeezer also. This is saying, you know, like I talked about before, we have this asymmetry if we can, you know, see up to 20, almost, we can even see 30 dB if we want of squeeze light generation, but we can't measure really beyond 5 to 8 dB of squeeze light. And the reason for that, again, is loss. And if you look at our loss budget really quick on the squeezer cavity loss is that bow tie cavity I showed you with the nonlinear crystal inside. And it does about 5,000 round trip passes through that nonlinear crystal. And for all of that, with the cavity enhanced loss, we have about 1.5% loss there. For the Faraday isolators, I don't know how many people here are familiar with Faraday isolators. They're equivalent electronically to like a circulator. So if people have used RF circulators or so, they're the optical equivalent of that. It's something that, the way physics people would say this, it breaks time reversal symmetry. So something comes in and then goes out a different port. It makes a difference between two directions. That's the job of circulators. So we have 5 passes through circulators, and each circulator pass is only 1% loss. So for, maybe this doesn't land with theorists or computational people, but for experimentalists to have a circulator with 1% loss is like amazing. We have the world's best optical circulators, and they're very highly customized for our application, and they cost like 50K each. Every time you want to pick off and control a beam, that's an issue. Every diagnostic you get is also a loss. Everything you have in the path, they're all losses. The photodetectors are also not perfect quantum efficiency. That's also a loss. Altogether, we have about 15% loss to be compatible with about 6 dB of squeezing. It's 4-fold noise power reduction currently. And so just to show you a little bit here, what happens if we fix loss? So we can fix loss. For example, we found that we had a damaged corner of our crystal that we were operating on. We can fix that by moving the crystal over to find another phase match better spot in the cavity. And that does this seemingly little jump over here. That actually lines up with when we get an additional dB of squeezing. So this is the equivalent of if we recover about 10% loss, we'll get an additional dB of squeezing. What that actually does here is it recovers about 5 to 10 megaparsecs of astrophysical range. That's a complicated statement, but just to put this into like context is that if we move a nonlinear crystal in a cavity by about 2 millimeters, we can extend our observational range by up to 10 megaparsecs. And for example, it's about 1 megaparsec to Andromeda. It's about 3 megaparsecs for the local group. The local supercluster of like 100 is about 30 some megaparsecs, and to the next supercluster is about 100 megaparsecs. So by this, we're extending our range by, you know, an extra 10 galaxies that we can search for neutron star mergers. So this is just what we can achieve by moving a nonlinear crystal by 2 millimeters and recovering 10% of optical loss in a cavity. Just to make that connection, it's kind of cool. And so for the future, getting pretty extreme in terms of what we are really demanding. If we want, again, 3 dB of loss, you can see roughly how dB scales with losses here. You just replace it. So you get about 3 dB of loss. You can get about 3 dB of squeezing. If you have, you know, 60%, let's say, efficiency through it, it's about 30% loss, you'll get 4.5. If you have 20% loss, you'll get 6 dB. That really means order 10, sub 10% loss to get 10 dB of squeezing. And that's where we're going for the future, and that's not even compatible with how we operate our observatories today. So this is very challenging. But you can see if we do get that 10 dB, we'll really clear quantum noise from most of the astrophysical band over here if we can get another 4 dB out. And for the future, you know, people want to build, like we were talking about 40-kilometer detectors, and that would be totally epic if it's possible, because then you could basically see every stellar mass black hole collapse. That is, you could see the remnant of every star that's ever collapsed in the history of the universe, which would be totally epic, because this could include even a population of stars that nobody's ever observed before, the first stars that ever formed. You might even be able to see their remnants with next generation gravitational wave detectors, which would be super cool. Okay, but again, what do we need? We need things like low loss optics and materials. robust noise models and diagnostics. And we need more dynamic control of back action across the band. And what do we get? This is a very cute video, I think, of just like a bunch of different detections. This is only the first 90 that we had from the first 3 observing runs. And so what we detected classically is kind of these guys. And then even before the current observing run where we detected 200 more, this was how much we detected by just the initial injection of squeezing. And now it's more than twice that. And then, so the LIGO scientific collaboration is huge. There's like 1,600 members, over 130 institutions, 20 countries. And I want to point out here that there's a lot of both California universities, but I want to point out especially Cal State Fullerton because they have such a great LIGO group there. And that's been great for our observatories. We have our group we're establishing at Berkeley. Sonoma State also has had a really, really important LIGO group in the past, and tons of like amazing LIGO people who are kind of, puppeteering a lot of the operation today, for example, came out of Sonoma State. I don't know if folks here have heard about Sonoma State and the temporary closing of their physics department, hopefully only temporarily. So it's been, challenging because they're a very small school, but many like really amazing superstars in LIGO who run a lot of things nowadays, came from, for example, Sonoma State, Cal State Fullerton. And so there's a long history, I think, of big collaborations and, that has a lot of synergy with, more teaching-oriented institutions. That's been a great way for, us to get really, really good people. So also in California, there's Riverside, there's Stanford, of course there's Caltech, which manages the observatories alongside MIT, of course supported by the NSF. Okay, let me just end there. There's some references if you want, but I think we're about time then at noon. Thanks.
So,
yeah, it's very big. They're doing site selection now. They're looking at a lot of different things. There are a lot of factors for site selection that I'm not privy to all of them, but there are many considerations to be made.
I just had one quick question. With your addition of being able to filter out some of this noise, right? You could have made a smaller LIGO and got those earlier detections, right?
It could not have been much smaller.
I was just curious, like whether that knocked that 2 kilometers down to,
Yeah, so the original, actually at the Hanford site, they were originally proposing a 2 and a 4 kilometer interferometer that were co-located. Anyways, didn't end up being a good idea, but they still have all the 2 kilometer stuff.
but with your additions, like with the 6 dBs of thing.
But I think, okay, so maybe one perspective I can take is it's great that squeezing worked, but it wasn't in the original plans for LIGO.
Right, I understand that.
So LIGO is always going to go towards whatever way we can to reduce noise and to increase strain sensitivity, right? So increasing arm length is a way to increase strain sensitivity. So you're always going to be pushing yourself to build the biggest thing you could possibly afford to build, essentially.
Yeah, but I guess I was thinking from the directionality standpoint, having more observing stations that were maybe smaller, less resolved, less, right, might allow you to say, hey, we did see the same signal. Again, it was noisier because it was on a smaller thing, but we know we are so far away from a bigger LIGO.
Yeah.
Right.
Yeah, that's an interesting conversation also right now with next generation observatories, because the official NSF recommendation was that if Europe gets to fund their next generation observatory, then the US should fund the 40 kilometer. But if Europe doesn't fund the next generation, we should fund a 40 and a 20 kilometer. So this is already a conference, that is already leaking into discussions for next generation. Next generation, they want to do a 40 and a 20 US experiment. But then it gets kind of into a global perspective of why wouldn't you just build one in Australia? Australia really wants to have a gravitational wave detector, but politically very challenging. So,
I think also we only have limited space on campus. Yeah. So could no.
Yeah, I mean smaller would be better, but I think facilities are you have one shot to build the biggest thing you can. So you go for the biggest thing you could possibly afford every time, is generally the style that it takes, I think. And something,
Well, I guess I was
Yeah.
thinking from being from a smaller university. But we have kilometers of land around us.
Yeah.
If you build something smaller, that can
Yeah.
at least say, hey, we could, we're a
Yeah.
data point of saying how we
Yeah.
saw what you saw,
Yeah.
and we're so far away from you, right?
Yeah.
There'd be some
Like,
value in that, right?
it would be,
Big resolved enough, like, hey, it
Yeah.
came from there as opposed to
yeah.
from there, right?
Yeah, like having more detectors is great. I guess part of the discussion is maybe like, what's the difference between 2 kilometers and 4 kilometers? Like, those are very different, but they're both a totally different game than 2 meters. Like, the amount that it takes to fund 2 kilometers is already, I think by comparison, yeah. It's like you could fund a cheaper one. And so that is, yeah, there's,
Cheaper ones, less resolved, but then now you start to get direction.
but to even get, yeah, so like for example, maybe an interesting point of comparison is like if you look at the global network, the European detector is 3 kilometers long. Virgo is only 3 kilometers. And that really helps that they exist. And for other reasons, their sensitivity has not been as good as LIGO. But yeah, so like it helps a lot to have that one, right? Like Kagra, the Japanese detector, it's only about 1 kilometer. And again, for other reasons, they're not as sensitive as they should be, but they're hoping to get sensitive enough to help with localization. I think you need to play it smart. So you need to be clever about how you do it. More sensitive is always better. But there are many routes to doing that. You can have more complex infrastructure that should theoretically be better, but due to technological challenges, it can never meet its design sensitivity. That is a very common outcome. To have a detector that meets design sensitivity, you already are kind of trying to do the minimum possible thing that you think will definitely work. Like there's a compromise, right? You can go cryogenic for the theoretical better in sensitivity you could get by cooling your thermal noise. Yeah, but that could make a big difference. The problem is that once you go cryogenic, you often have to introduce a lot of vibration noise in order to maintain the cryogenics. And then it's kind of a shooting yourself in the foot thing is what it comes out to several times. So there's a like for big, complicated, and like high precision things, there's always like a straddling with risk, right? And this is like another good maybe perspective on quantum sensing. Like the squeezer is extremely low risk. Right? We're a completely separate laser that's in a different thing on a different table than all the other lasers. Like operationally, they could cut us off, and nobody would ever notice. Like it doesn't burden the main facility to add a separate injection of squeeze light that we're aligning on our own. Like that's a self-contained thing. If the squeezer blows up, it doesn't matter. You'll just valve it out, and nobody will ever like. It's not a big deal. But that's part of why it's like genius, because it the backup option of, oh, it didn't work is it's okay, I'm just gonna valve it out, right? So it's low risk. It's high reward, but low risk. It's hard to find things like that. Usually if you wanna do something like theoretically better, like cryogenics, it's a big risk when you do that. Just some perspective. Yeah.
So I think this is kind of just solidifying a thing that was just asked, but like, not policy or designing experiment wise, just out of curiosity. So you had the first run without any squeezing, you detected like 10 things. Mm-hmm. Now that you know your squeezing works and everything, how short could of that first run be? Like how shorter could the arms have been with squeezing and still seen the same? Basically, if you went back in time and had have made that separate decision, would you still got the Nobel with like a kilometer or 3? Like, is there obviously rough estimate?
I think the SNR was good, but not that good. I think it was, our threshold to claim a detection is an SNR of 8. I don't think it was, I can't remember what it was. I think it was like 12 or 16 or something. It wasn't that good in some sense. Like it wasn't so good that we could have easily lost a factor of 2 and been confident.
Okay.
I have a sort of question, confusion, because this is not my area. My understanding, you're having this discussion about noise.
Yes.
But my understanding that when you're talking about noise, you're talking about two type of noise, because quantum noise are noise that is inherent to the system. You can't remove it. You can, so like for instance, you can do squeezing,
Shove it
and
around.
if you mess with the exposition,
Yeah.
then you change it
Yeah.
in the
That's exactly
momentum,
it. Yeah.
in
Yeah.
the momentum phase.
Yeah.
So I guess I am confused. How are you able to reduce it in the way that you're saying that you can make these precision measurement?
Yes. Yeah, that is a very good question. I think Justin actually had a really good hand wavy argument for it yesterday. If you want to repeat that hand waving, I thought that was actually really good. So the question is, I think maybe one way to phrase it is like, what does squeeze light do? It produces correlated photon pairs. But then the question is, how do correlations within the noise affect the measured noise that I actually see in real life? Right? Like, how do correlations in photon pairs change the noise properties of my signal? Is that one way to, like, reframe the question? Okay, that's like one way maybe I interpret your question is like, what we're doing is producing correlated photon pairs, and we sync that up to the main light that we are measuring. Justin, do you want to repeat your hand waving argument of how do correlations affect measured outcomes?
I don't know if I can do it with my like diagram. And I'm not 100% confident that you're asking that I'd be answering your question, but I think you. I'm really hesitant to say this. I think you're essentially measuring amplitude. You're measuring the photons to get a sort of position measurement of a mirror, yes?
Yes.
And you're sort of not concerned about one of those two conjugate variables, but knowledge of one gives you information of the other. So you can kind of put all the stuff you don't know or care about, you can add uncertainty there, and it kind of removes it from the other thing. Were you talking about the GRA stuff?
Yeah.
And the quantum optics
Yeah,
thing?
yeah.
You can do all the signal photon stuff we were doing in the lab with the one arm of those, but you have to get information from the other arm to influence how confident you are in what you know in the other arm.
And I basically start playing like this in one side of the laptop, and I create very violently in the next side.
Yeah.
Right? So for me, even though everything here seems calm, I've created a mess far over here. So aren't you not changing the system? So you're basically saying, yeah, I get good results here, but by messing up there, the correlations that are involved now basically have shifted. So to me, you're really not getting the true information of the system. You're getting the information that you basically project into the system.
We don't care about side. We don't care about
The-
I don't care about
No, but you see what I'm saying, yes, I understand that, but the only reason why that is doing what you do is doing over here is because of what you did over here.
I don't care about side. That's why you voted for me. I don't care.
Yeah, but we did something over here. In other words, it's like when we talk about biases, right? In other words, I already bias the system, right? It's almost in quantum mechanics when you say in a loop.
Exactly,
Right?
yeah.
That's what we tend to mean by measurement, and that's why we still have a measurement problem.
I think maybe for this, the way that I think about it is more, we're engineering correlations in the noise. That's the essential thing that we're doing, right? So the question is like, how does engineering correlations change your noise, right? And what you're doing with squeezing is you're generating photon pairs exactly like you saw yesterday, right? Where you basically you pump the crystal, right? And then there's two kind of like light cones, right? Of the two photons, the signal and the idler photon that could come out of this nonlinear crystal, right? And ours are the same, but it's the same physics, right? And then what you're getting is you say, okay, I'm gonna measure this photon on the left, right? And I'm gonna use that and see whether on this arm another photon clicks here, right? So what you're looking is, if I detect a photon, is there a correlated photon here? And that is essentially what you measure in squeezing. It's the signal and the idler photon. That's the two photons that come out of it. And what you're saying with the correlations, for example, if you're, I forget the anti versus correlated. If you're anti-correlated, if I click here, I always click here, right? But if you measure the two photodetectors individually without having correlations, like there's just some percentage chance you'll measure on A and some percentage chance you'll measure on B. If you introduce correlated photons, you can guarantee you always click on both, or you always only click on one, something like that, depending on how you engineer the correlations in these photons. But it's about engineering correlations within the noise to, for example, click here and always click there. And for something like shot noise, because what that is a statement of how many photons do I measure per second ambiently. The amount of photon clicks per second is what you're trying to engineer. I'm sorry, squeezing has a very awkward words description compared to mathematically. But it's, yes. I don't know if that makes any sense at all.
It makes sense. I went to University of Arkansas because one of the architect of it is May Shaw.
Yeah.
And
Yeah.
he was at University of Arkansas
Mm-hmm.
at the time. So
Yeah.
There was a lot of excitement
Yeah.
about squeezing. So,
Yeah.
but I never really understand it clearly.
Yeah, it's more or less about correlations with engineering the correlations within the noise. Yeah, I don't know if that's, sorry, that's not a more clear statement. Mathematically, it makes a lot of sense, but definitely describing it in words is a little bit awkward still for me. Yeah.
All right. Any other questions to follow that up before we break for lunch? All right. Let's thank Vicky again. Then we'll